Welcome back to Problem Corner, another edition of this newsletter piece that is put out in conjunction with the International Group for Mathematical Creativity and Giftedness. The editor of the newsletter is Scott Chamberlain from the University of Wyoming and does it in participation with Associate Editor Chris Weiss out of Ohio University. So we are to the Problem Corner solution for this September 2025 newsletter number 25. If you don't know about the International Group for Mathematical Creativity and Giftedness, you can check them out at IGMCG.org. I will also link somewhere over there, somewhere there's going to be a little thing you can click and it will let you go to their website to check them out. They do have conferences around the world. Their next conference is next September in Calgary, Canada. So if you happen to be in Canada, maybe that's something you would like to check out, or maybe you'd like to make the trip there to be a part of that conference. So I got an email last time. Oh, by the way, I do have a little bit of a lisp. I got a new orthodontic device in the back of my teeth, and it makes my S's and TH's not quite come out correct. So you'll have to deal with that. Source, the 38th Latvian Open Mathematics Competition, which was held in 2011. And the problem is problem number 4 for grade 10. So why this problem? I've done all AMC problems up to this point, or AIME, they're American competitions. And I'd like to kind of start branching out. And luckily enough, I got an email from my friend Andres in Latvia. And so he had shared a problem with me, and I thought, hey, it was really cool of him to reach out. And I thought, I'm going to pick my next question from the Latvian competitions that are there. And I'd also like to ask you, if you're residing in a foreign country and you know about competitions in your country of residence or where you live, your background or whatnot, please send me an email. I will choose the next question for the Problem Corner from among the nations that reach out to me, or people from those nations or countries, and I will then decide after I get enough of them in which country I'm going to go with. But you can tell me a little bit about the competitions in your country. I'd love to learn. I don't even really know that much about all of them, but I'm sure there's a lot of wonderful ones out there. I'd also not yet done a proof. And so we're going to try and go through this. I'm not the best at proving. It's not something that I teach on a regular basis, but I'm okay. I'm adept. Just not like, it's not my forte to teach it all the time. So a regular 9-gon and a regular 10-gon, a nonagon or decagon is possible as well for words here, are inscribed in a circle. Their vertices divide the circle into 19 arcs. Prove that there is, did I miswrite this? There is, let's fix that right now, that there is an arc that does not exceed 2 degrees. Well, that's a shame over there. Gonna proofread before I start the video next time. Prove that there is an arc that does not exceed 2 degrees. So a little bit of background about my channel. My predominant audience are those students who take the American math competitions, also called AMC 10, 12, AMC 8, and the AIME. As such, my audience is primarily 6th grade to 11th grade. Although there are older people as well, but the big chunk, probably 80% or 70% or more, are going to be high school and middle school aged kids. So as such, I'm not just here to do a solution. I also want to talk about the framework of the thought that we put in. What are the ideas that we generate? A lot of times when we start problems, we don't know where to begin. And so I'm going to kind of walk through my own process that I did, on my paper when I was trying to solve it, and kind of talk about what that process looks like, because I would like my students and those students who are watching to be more comfortable in the open space where there's not exactly a definitive way that you're supposed to start. So this might not be the most efficient, but it's how I developed a framework for how I will try to prove this. I did not consult the solution for this, although there was one available. I still haven't looked at it. I know that this is probably an acceptable way. We know that it's true because you're proving it, and they wouldn't ask you to prove it typically in most competitions unless it was actually true. So let's go ahead and get started. I didn't know where to begin. Okay, well, maybe we'll do this. Maybe we'll say that our circle is on the positive x-axis, right, at 0 degrees. Okay, so we start that 0 degrees like a unit circle. I do have a stutter, by the way, and this device makes it come out. I don't usually have it when I don't have the thing on my teeth, but it was really bad as a kid, and it got a lot better thanks to speech therapy. So anyhow, so if you start at 0 and you're on the decagon, let's say, then every 36 degrees, 360, divided by 10 is going to be every 36 degrees, you should find a vertex. So you can go, 36, a little bit less than 45, 72, 108, and so on. I didn't really feel the need to draw them after that, but sometimes I like a little pictorial reference to kind of help me feel comfortable with what I'm doing. And from here I said, let's just list them out. So I said it'll be 0, 36, 72, 108, 144, 180, 216, 252, 288, 36 more, 12 and 24, 324, and then obviously you'd be at 360, which is right back to 0 again at that point. So after I wrote these out, in fact, why did this one lonely number over here, let's just put it over here. We should be good. And we will put 0 again here because that's where you're going back to, even though it's really the same point. Okay, so then I said, all right, what might I do? How would I prove this? Maybe algebraically. Maybe we say that the first vertex of this 9-gon, we'll call it located at x, but we don't know where x is. So this is the exploratory phase before you know what you're going to do to create your proof. You're trying to get ideas by, trial and error, by experimentation. And that should be something you're very comfortable with. Most of the best solvers don't know what to do in the beginning in problems like this. They just kind of try things out and they discover things, and then they use their discoveries to form an idea about how they'll go about their plan. So then you're going to say x, and I could say it's got to be greater than 2. We're trying to create it, we're trying to prove it wrong is what I tried to do. And I thought maybe by trying to prove it wrong, we could prove that it's impossible to prove it wrong, something like a proof by contradiction. So I say, let's assume that x is between 2 and 34. That way it's more than 2 degrees away from 0 and from 36. And I thought, for now you could just call it 3 or something, right? And then essentially you're going to be doing what? Every 40 degrees you'll have a new number because you have a 9-gon, right? And so you say, maybe I could also do this. Maybe I could place the 9-gon with its vertex also at 0 and then turn it like a knob so that it will then move its vertices all around. And you kind of think of it like that overlay in a way. So maybe I'll just start with that. I'll go 0, 40, 80, 120, 160, 200, 240, 280, 320, and 0, and then I'll just add something to this, right? Maybe some amount, x, that's between 2 and 34. So if I did that, you could just say you're adding 3, for instance, and you could go 3, and then just offset all of these, 43, 83. Now I know I don't technically have to write them, but I don't quite yet know what I'm doing in my proof. So as you can see, I had a lot of these little kinds of ideas on my proof here that I had to kind of look into and see what would go on. And so I said, all right, I did it with x, but here I'm just picking a number to use, just an arbitrary value, like a test value. And you go 123, 163, 203, 243, 283, and then if you add, you're at 323. Wait, 1, 2, oh, that's these ones, yeah. So now if we compare these, I was thinking they were those, and I was like, but wait, they're all good, it's working. But I wasn't actually looking over here at these ones. And so where would this 3 be? It'd be somewhere between 0 and 36. And the 43 would be in here, the 83 would be in here, the 123 would be in here, your 163 will be in this gap in between. And so you say 203 will be in this range, 243 will be in between here, 283 here, but sadly 323 is within 1 degree of 324. And not really sadly, because we know this is going to happen, we anticipate it, but we were kind of hoping maybe we could find something or disprove it, whatever. And this is the one that fails. So you say, but is it only failing because I chose x to be 3 degrees? Maybe I could pick a better x value and suddenly it wouldn't fail to occur. But it was in the process of placing these in between these gaps, I started to think about how the nonagon would go in between the gaps of the decagon. And so how many gaps does the decagon have on its arc? You can say that between 0 times 36 and 1 times 36, you have 1 gap. So if I just go to the end, this is 9 times 36, and this would be 10 times 36 when I go back to 0. So there should be 10 gaps. Logically, 10 gone, 10 gaps, 10 vertices, because there's 10 sides, and each of the chords of the circle that makes the gap is going to be a chord of the decagon. Okay? Various ways to think about why that is, and many of us just know it off the top of our head, but just to kind of demonstrate a thought process. So if I've got 10 gaps, I've only got 9 vertices on my 9gon. That means there's going to have to be a gap that we skip and we don't put anything in between. And that made me reminded me of this problem, 2021 Fall AMC 12B problem 19. In this one there was a 7-gon, 8-gon, and 9-gon. I was able to solve it in like 30 seconds by just visualizing what would happen as you place the vertices around the circle. But it was thinking about the gaps where the different vertices of the different 7-gon, 8-gon, and 9-gon would fall. And I drew inspiration from this problem solution process to think about what could be going on here. Maybe we can focus on the gaps. Since we're going to have to skip 1 gap, it doesn't really matter which gap that we skip. That would be arbitrary based on what our first value was in degrees. We could say that there's a gap of 36 degrees, and if we go backwards 2, right, and you add 2 degrees here, and you go forwards 2, what is that total gap? Now, between here all the way to here, it's exactly 40 degrees. And if you go inside of this one so that you can go outside of that one, you're going to be within 2 degrees on this side. If you try to put that vertex back a little bit here as you're skipping the 36 degree gap of your 10-gon, then you're not going to be able to do that either without moving it within 2 degrees. Note it says does not exceed 2 degrees. So 2 degrees is part of allowable. Meaning if you're right here on that 2 degree mark away from the vertex, you have not exceeded 2 degrees. And the only way that you can go outside of this bound is if I move inside of this bound. And the only way that I can go inside of this bound to get outside of this bound is to be within 2 degrees on the other side. So there's simply no way around it. You're going to have to be within 2 degrees of one of the vertices on the regular 10-gon. So that was my solution process. That's what I did to come up with one. Maybe you had a great one as well. Maybe the official solution, which I have not looked at, is more refined than what I'm putting out in this video. But that was the general process. I hope you enjoyed it. And once again, if you're from an international community that has contests in your native land, please reach out to me by email. My email is in the newsletter, and I will gladly pick something from any foreign nation that I can translate into. This was not in English. I just used Google Translate to be able to translate it. Before I heard back from Andres, I was actually looking at Estonia, but when I tried to translate Estonia, there were some parts Google Translate couldn't do, but I think most of them I can probably be able to translate. So, hope you enjoyed it. See you in the next one. Don't forget to check out IGMCG.org. They're a great organization that helps students and people from around the world in the realm of mathematics, and they do a lot of things. There's a lot of them that are out in various nations performing many different activities and they share them in the newsletter and things like that, and they have conferences where they talk about what was effective here, what was effective there, and people take these pieces of information and go back to their native lands, and it's a great way to share and experience mathematics all around the world. That's probably not the way they would describe themselves. That's my rough synopsis of kind of what I've gathered, and just an aspect of what they do. I'm sure there's so much more to it. You should check them out and consider becoming a part of their great organization. Hope you enjoyed the video. See you in the next one.